Yeah, first I want to thank Professor Crispino to let me talk about this work that it has been done in collaboration with all these people. That includes Miguel Alcubierre, Juan Barranco, Argelia Bernal, Alberto Diez, Carlos Cerdero, Miguel Begevan, Darío Núñez, Víctor Jaramillo, Nico Sánchez Gual, and Oliver Sarbach. And it has become a big project. And this boson stars is a new family of compact objects that generalize, in some sense, the mini boson stars in the following way. They are formed with several scalar fields. So the basic model is to assume there are some complex scalar fields with certain mass that are coupled to the Einstein gravity, and they are coupled minimally to the gravity, and they possess a stress energy tensor. And the interesting thing is that the sum of the stress energy tensors of each scalar field, the sum is spherically symmetric, even though each of the stress energy tensor of each scalar field is not spherically symmetric. So this is a nice combination among the fields in such a way that they allow to an static and spherically symmetric solution of the spacetime. And each field satisfies its own Klein-Gordon equation. The model is built as the mini boson stars, and that is that we assume that each field has the harmonic time dependence, and we make a decomposition in terms of the spherical harmonics, and we assume that the spacetime is static and spherically symmetric. So we write the ansatz for the metric in that way, and we write the Klein-Gordon equations in that symmetry, using alpha and, well, the lapse function and the radial component of the metric as variables. In order to find these equilibrium solutions, the real frequency becomes the full system becomes an eigenvalue problem, where the frequency of the field becomes the eigenvalue. And the solution of mini boson stars is recovered when L is equal 1. That means one single field. And this is a common limit. So I mentioned that we have several fields. That is, each field is labeled by an L number. And this L number is the angular momentum number of the harmonical spherical functions. So it's kind of an angular momentum, but it's not a rotation because we have spherical symmetry. But still is an eigenvalue of the Laplace-Beltrami operator. Well, the system, the full system that I put in the previous slides have some scaling properties that allow us to have many solutions, in the sense that we can use the mass of the scalar field as parameter, as a length. So the frequency scales with this number and the radii and the amplitude of each field. And as a quantity to measure, to have some control, some measurements of the configuration, we use this Misner-Sharp mass that at infinity converges to the ADM mass. Then we also characterize the stars by its radius that we define as R99 radius. That is a common definition. That is the radius in which the configuration reaches the 99% of the total mass. And the interesting, the trick that makes the full configuration to confabulate to get a spherical symmetric configuration is that all the fields must have the same amplitude. So even though they are not spherical, if they have the same amplitude, then we can build this kind of stars. As I mentioned, we characterize, each solution is characterized by its mass and its frequency. So in the plot of the left, it is shown the mass and the frequency. The black line represents, each point in the black line represents a solution, and this is a typical curve in boson stars. They have a maximum that is labeled with A in the black line, and the behavior with L, including several fields, is that the maximum mass increases and the frequency decreases. And actually, the compactness changes. As L increases, we have more compact configurations. That is shown more or less in the right plot, in which we have the mass and the radius. So the effect of increasing L or increasing fields is to increase the mass, but also the compacity. So the stars do not grow linearly, but they grow in a certain way in which the compacity grows. In the left, we have the plot of the metric coefficients. In the bottom is the lapse, the radial function, and the density for L equals 1. And as I mentioned, the compactness grows as L grows. In the plot in the corner, in the right corner, is the same, the mass versus the frequency, and we see the behavior with L. And in the table, in the plot, there are some marked dots that are labeled with A, B, C, D, and E. And these will become important in the following slides, because we were interested in knowing the stability properties of these configurations. Because since I told you that each field is not spherical symmetric, one may think that this configuration is highly unstable because, it seems that it was fine-tuned to get the whole spherically symmetric configurations. Then another property that is remarkable of these solutions is the energy density, the geometry. The geometry is spherical, they are spherical, however, the density has this behavior. For the mini boson star case, that is L equals 0, the maximum of the density is at the center. However, for L equals 1, the maximum of the configuration is not at the center. It has moved to the right, off of the center. And as L increases, the maximum gets away from the center. So the density tends to be pushed towards the surface, and the stars become more like shells. Instead of balls, with the maximum at the center, the maximum tends to be at the surface. As I mentioned, we were very interested in studying the stability properties of these stars. And what we did is to follow some of the standard procedures to study that stability. But since we have the machinery to make numerical simulations in full GR, we took as initial data these stars we found and perturbed them. And what we found is that they behave in the same way as mini boson stars, in the sense that stable configurations remain stable under spherically symmetric perturbations. In the following, I will concentrate on these kind of perturbations. They are spherical. So the configuration is spherical, and we perform spherical perturbations. In the end of the talk, I will say something about non-spherical perturbations. So the fate of the stars is that, to summarize, stable configurations can divide in two types, stable and unstable, depending if they are in the right or in the left in the plot of the mass versus the frequency. It is known that that point, the maximum mass, splits the families of boson stars. However, the stable configurations under spherical perturbations remain stable. Configurations that are in the unstable branch have several fates. They can migrate towards unstable configurations, they can collapse towards a black hole, or they can disperse. And that behavior is related with the binding energy. The way in which we perform these equilibrium states was the following. We started with a solution, an equilibrium solution, and then write the Klein-Gordon equation using the 3+1 decomposition, the usual one used in numerical relativity, and we perform the evolutions using a modified Baumgarten-Shapiro-Shibata-Nakamura formulation that has been used in many scenarios and has been proved to be very stable. Then we decompose the field. We separate the kinetic part, that is encoded in this pi function, and in this chi function, that is the radial derivative of 5. The energy density is the one measured by the Eulerian observer adapted to the Cauchy surfaces. We classify the type of perturbations that we did in 3 types. The first one is considering that is an internal perturbation. So we put some small amplitude inside the star, but it has the property that the density energy of the star changes. In a second type, it's still internal, but what is perturbed is the kinetic part in such a way that the mass of the configuration can grow or diminished. And finally, the third type of perturbation is one in which there is an external perturbation. So as a pulse comes into the star and hits the surface, and the star begins to oscillate. And the amplitude that we chose is a generic function that is given by this Gaussian perturbation. Some quantities that we use to make some diagnostics in the stars is the number of particles that is given by this expression. This is the density of the scalar field as measured by the Eulerian observers. We define the binding energy, that is the difference between the ADM mass and the rest mass of the star, that is computed by this number times the mass of the particles. And also, as I mentioned, we expect to have the formation of a black hole. And to have an idea and actually a measure of the size and the mass of the black hole, we compute the mass through its area in this way. Again, this is a plot of the mass versus the frequency for a representative case that for L equal 2, that means 3 fields. We have several configurations. 1A that corresponds to a star in the stable branch. A configuration B that is on the unstable branch. However, the binding energy is positive. And then configurations C and D corresponds to configurations in the unstable branch, but are unbounded in the sense that the binding energy is positive. We start with an initial data that with these equilibrium configurations. We use it as an initial data, but in order to add the perturbation, when we add this new, this small amplitude to the field, that configuration is no longer a solution of the Einstein equations. So we must solve again the Einstein equations, including that perturbations, so in order to make consistent the evolution. Then after some period of relaxation, what we got is that after some time, the stable configuration, A, this is the lapse function. It's a bit perturbed initially and then remains. This is a signal of the stability of the solution. And this in the right plot, it is the amplitude of the scalar field versus time. So we see that oscillates, but oscillates around central value. On the other hand, configurations that we suspect are unstable and tend to migrate because the binding energy is positive have this behavior. The lapse function oscillates but changes compared to the initial value. So you may see that at time equals to 0, it has a value, but then acquires another value. And also in the plot of the mass that is in the bottom, initially it has some value, but then it starts to decrease. Configurations that we suspect that they will disperse because they are in the left of the maximum. They are in the left of the maximum mass, and also they have a positive binding energy, behave like this. The lapse function, its minimum, has a value at the beginning, but then tends to 1. And 1, well, exactly 1 corresponds to Minkowski spacetime. In the right plot, on the top, what is shown is the amplitude again of the field. And what we see is that at the beginning there is some maximum value, and after time goes by, the amplitude decreases, tending to 0. And the mass of the full configuration has a similar behavior. It has a maximum at the beginning and then disperses away. So this is this is the behavior, the usual behavior of a configuration that has been destroyed. For configurations, we expect there is a black hole formation during the collapse. And this is what happened. Again, this is the minimum of the lapse function, acquires some value at the beginning, but then collapses. This is the phenomenon known as the collapse of the lapse, and it's very typical when we have the formation of a black hole. But actually, the proof that we have found a black hole is the rise of the apparent horizon. We see in the plot on the top that at the beginning we don't have anything, but suddenly an apparent horizon emerges. And that is the indication that a black hole has formed. So this is the fate of these L boson stars is the same or is similar as the mini boson star relatives. We have some of them that are unstable, stable, and the unstable they have some subfamilies that may collapse to form black holes, or may disperse, or migrate towards an unstable configuration. And that depends on, as I mentioned, depends on the value of the binding energy. But in this plot, the mass versus the frequency, we can separate the families and actually mark each point of transition. In the dark points that are joined by a black line in the right is the minimum of the binding energy. That is the maximum of the mass. The points in the left, black, represents the values in which the binding energy is 0. Then we have these plots separated in 3 regions. And these are parameterized by the value of 5-0. That is the value of the field at the center. Remember that as L increases, this value goes to 0. However, there is a correspondence between this value and the frequency of oscillation. Then configurations that are in the right, in the extreme right, they are almost Newtonian, are stable. Configurations that are in the middle are unstable, but some of them will collapse or migrate. Whereas configurations at the left will disperse or collapse. One of the questions that emerged during these studies was how stable are these stars with respect to non-radial configuration, with non-radial perturbations. Because as I told you, it seems that they were very fine-tuned, the amplitude was very fine-tuned in order to get an spherical, the spherical shape. And as I show you, the density is not spherical, but tends to move towards the surface. Well, I say that it's the surface, but since we have a scalar field, boson stars don't have an actual surface. They are characterized by this R99. The point is that the density is not located at the origin. Then what we did is to try perturbations that are not spherical, but basically we were looking for some instability that is known in neutron stars, that is the so-called bar mode instability. Since neutron stars rotate, there are some modes in which these modes grows and the stars may be destroyed. So we tried to perturb our solutions with this type of, looking for this type of instabilities. And what we did is to perturb the energy density in that way. So trying to perturb in this direction, well, if this is C, X and Y, we perturb in this direction. So probing the stability in this, along this axis. And a way to measure the deformation of the star, we define those quantities in terms of the moments of inertia that are defined in a local frame reference. And then we perform, again, numerical simulations. We start as initial data with the equilibrium configurations. We perturb them in this way, in the density. We solve, again, the Hamiltonian constraint and evolve. And what we see is that they remain stable, but we found something. Well, they remain stable under these kind of configurations, but it became very difficult to say if they are the same stars that we start with, because due to the oscillatory nature of the scalar field, the configuration in 3 dimensions, once that starts to oscillate, is very difficult to reach a stationary state. And this is well known in boson stars. And this is because of the nature of the scalar field. So what we could say is that we didn't find some growing modes, in the sense that unstable, the stars that we suspect were stable or are stable under spherically symmetric perturbations, they don't have these bar mode instabilities. So in that sense, they are stable. And well, this is something that I already said. The time scales to reach a stationary solutions are very difficult to find, and especially in these 3-dimensional evolutions. However, we can say safely that if they are not the same spherically symmetric configurations, these L boson stars are points in which the whole space of solutions of boson stars tend to converge. Finally, well, these are the conclusions. These L boson stars are stable. At the beginning, we proved they exist. We found the solutions and characterized them in terms of this L parameter. We studied the stability and we found that numerically, we found that they are stable, but actually we were able to prove analytically that they are stable on the radial perturbations. And that is quite straightforward to make such a proof, just having the configurations and assuming that we perturb and the modes, well, if the configuration is stable, then the modes do not grow, whereas if it is unstable, the modes will grow. And that is more or less easy to prove. No, well, and we did it not only numerically, but also analytically. Then we tried to study the nonlinear stability again, but this time using non-spherical perturbations. And what we found, or what we can say, is that for the time that we last the evolution, they remain stable. And that's it.
Okay, thank you very much, Juan Carlos. We have time for 1-2 short questions.
Thank you, and thank you for a very nice talk, Juan Carlos. So I have perhaps 2 questions. So okay, it's a package of one, but so you have this number n, so which is number of fields, right? And it can be very large. So how? Yes.
Capital N.
Yeah, capital N. Yes. So how large can it be? There is no upper value. So how
you can put as many fields as you want.
In practice, so for the simulations that were made, what was the maximum number, more or less?
For the simulations,
yes,
3 fields.
3 fields.
We got up to 5.
Okay.
But when we prove the limit of L tending to infinity, we try up to 100.
Okay. And regarding the stability, so I guess the stability of the solutions, even the radial one, depends on where you are on the spiral, right? So if I understand correctly, if you always stay more on the Newtonian side and take this capital N to infinity, in principle you can construct a very thin shell configuration that is stable. Interesting. Yeah.
Yeah, because the behavior is the same. As L increases, the curve just moves, but it remains in its shape.
Yeah.
There is an unstable region and unstable region.
Yeah. It would be funny to see a dynamical video of this.
It's kind of boring.
It's in work. It's boring.
Well, it's difficult to perform it,
yes,
but it's boring because what you see is just the field oscillating.
Yeah, but if it's a very thin shell, it would be well.
Again, it's like an onion. It's a spherical. It's spherical, just that the density is very near the surface. But it's spherical. It doesn't have these interesting shapes. At the beginning, but in the end.
Okay, so Juan Carlos, thank you for your talk. So I would like to know if you have any hint on how to generalize this for a collection of Broca fields.
We tried to do it, but Eugene knows because he gave us a hint to look, and it didn't work in the same way. because in the Proca field, we have an extra equation that is the constraint. And this decomposition in terms of the spherical harmonics didn't work.
So I guess you don't know how to change the ansatz, right, in order to get a spherical symmetric solution in the end. Okay, thank you.
Any question online? If not, let's thank the speaker again.